Hello guys, how are you doing? Hope you're all doing fine and good. I know we are all aware this is not the best period, it's tough times. We are asked to make efforts to, stay home, minimizing social relationships and so on. You can imagine that especially for you young guys, this is not, the best moment. But all these efforts we are required to make are necessary, and so please continue. It's for a good cause, and if we make it, we will come out even stronger from this situation. I'm sure about it. So please keep staying safe, keep staying strong, keep staying healthy at your houses, and of course, I'm extending these hopes that all of you are good and strong, also to all of your families and friends, wherever they are in the world. Hope they're all fine. Okay, after this short and necessary introduction, I would like to tell you something today. And in particular today I would like to show you and to go through a notebook that I've already uploaded in the beginning of the course still. The name of the notebook that you can see here in my screen is called Cross-Validation in Practice, and it's a notebook that you can find in the model selection lecture which I uploaded in the beginning of the course. If you open the zip file of that lecture, you will find two notebooks. One of them is the actual notebook I went through the lecture, which is called Model Selection. The other one is called Cross Validation in Practice, precisely. And if you remember, actually, I never went through that notebook, so you shouldn't remember this. But the thing is, my idea was to leave, this notebook and this short lecture as a sort of appendix. It's more like a practical than theoretical lecture. So my idea was really to talk about this towards the end of the course, which still is. I mean, we can already say we are in the end of the course. But given some facts, I was thinking that maybe it's better to talk about it a bit earlier, so now. And the reason being, first of all, that this can help you with the solution, with the answer of one of the questions of homework 3. In particular, question 4, you're asked to comment some code with scikit-learn, like written in scikit-learn, and some of the concepts that are in that question. I didn't really go through them during lectures, although I believe that if you follow the model selection lecture and read the notebook about that, then also that question becomes easier to answer for you. Furthermore, I already uploaded these notebooks of cross-validation in practice already those times. So if you have read it, and it shouldn't be too difficult for you if you have understood the model selection lecture, then if you have read it, then also the question should be quite easy if you have read it and understood it. So the reason why I'm doing this is indeed to make sure that you understand what is said in this notebook, also to help you with the lecture with the question, I repeat, of homework 3. Another reason why I'm doing it now is because the final assignment is approaching, and so maybe it's good that you already digest the concepts that we're gonna see with this notebook. Yes. So the thing is, this notebook, I repeat, is gonna be this short lecture. It's not gonna take too much time. It's gonna be more like a practical than a theoretical lecture. You will see a lot of code. I mean, not too much, but more code than text, let's say. And the reason is that I want to show you how to perform some model selection steps in a more practical point of view, okay? So we have already seen cross-validation, model selection during the model selection lecture. If you don't remember some of these concepts, please pause this video, go back to that notebook, and read that lecture again, because some of those concepts are useful for this one lecture in particular. Okay, so other concepts that you might need to know for this lecture are the difference between grid search and random search. In particular, we're gonna see several examples with grid search, although in the very first example we will also see an example of random search. But of course, all the concepts that we're gonna talk about with grid search can be easily extended if you decide to use random search. And just as a quick reminder, I always suggest you to use grid search for model selection whenever you have to tune not more than 2 or 3 hyperparameters. Okay? As soon as you have a large number of hyperparameters or a large range, of values for the hyperparameters onto which you have to search, then go with random search. Okay? Possibly with a large enough number of iterations. Okay, other introductory elements are okay, so we're gonna see this notebook is called cross-validation in practice, but of course, if you decide to use the holdout method, or for example leave one out cross-validation or group fold cross-validation, all other model selection methods that are mentioned and discussed in the model selection notebook, the principles are the same. So if you decide to go with holdout method, the principle that I report in this notebook for cross-validation are exactly the same. You should extend them also to that model selection procedure. Okay, and a very last requirement for this lecture that you need to know before we start, you need to remember at least, is the use of pipelines in scikit-learn. I'm gonna explain quickly. Pipelines are scikit-learn tools that allow you to chain several operations in just one object, okay, one scikit-learn object that can then be used as a normal estimator if we decide to run, for example, cross-validation with it. We discussed pipelines only for transformers in the data preprocessing lecture. So once again, if you don't remember these concepts of pipelines, please pause this video, take that lecture, take the notebook of that lecture, and check out the part concerning pipelines in scikit-learn. Okay, and today we're gonna see pipelines where we have transformers, okay, so for example data preprocessing steps combined with estimators, all right, so that we can create a unique object and then run cross-validation with it. But we're gonna see all of this with the due time. Okay, so let me just make a summary of what we're gonna see. We're gonna see 3 examples of cross-validation. In the first one, in which we use both grid search and random search, we see how to use them when we have more than one hyperparameter. Okay, actually, during other lectures of the course, we have already encountered how to perform cross-validation with more than one hyperparameter. The reason why I report it here is because, if you remember, I uploaded this lecture still, this notebook, in one of the first classes of the course, in which I only showed you how to do cross-validation with one hyperparameter. And so, of course, if you have read this notebook, this is or the notebooks about the other lectures, for instance SVM, or neural networks. This shouldn't be anything new to you. But just for sake of completeness, I want to represent to you this example again, like this example with more hyperparameters, just to show you more in detail how to do it. Then a second example, we will see how to perform cross-validation with grid search, but I repeat, it can be extended also to random search or to a holdout method, for example, if you don't do a cross-validation and so on, along with data preprocessing. And I'm also going to explain to you why we need these steps. And last but not least, we will see also how to compare two estimators, for example, but it can be also 3 or 4 or 5 if you decide to use more estimators, with cross-validation, and also with these pipelines in order to chain different operations with different estimators. Okay. For all these examples are going to be shown with the wine dataset, which is a dataset that comes with the scikit-learn library. It's a dataset in which we have recorded some characteristics of different wines. In particular, we have 124 wines in the training data and 54 in the test data. And we have 13 features, which are listed here, for each of these wines. Now, the goal here, we are in a classification task. The goal here is to try to classify these wines based on these characteristics, based on these features. And the classes, which are not specified more in here, but in theory, for this dataset, the classes should denote from, so these wines are all Italian wines that come from 3 different regions. And the goal is to try to see if, given the characteristics of the wine, we can find the regions, we can predict the regions, so the classes from which these wines come. Okay, so in the rest of this section, I just do some data exploration, as I expect you to do, or a part of what I expect you to do also when you do a real analysis. Okay, so for example, look at the correlation metrics, try to interpret it. If you write a report, always try to interpret what you see in the plots. Then we see the distribution of the classes, and as you can see in this case, we are in a almost well-balanced case. Okay, the distribution of the classes is quite even, not perfectly, but I will say that we are not in an imbalanced situation. And then we see what types of features we have. We see we all have, like all the features we have are all continuous. And last but not least, we also see that there are no missing data in the dataset. Okay. All right, so yeah, we should also check what I am not doing here. We should also check if we need to rescale the features. If I'm not mistaken, we should, but this is something we're gonna see in example number 2, how to do it. Here in the first example, I just want to show you how to do cross-validation with 2 different hyperparameters, okay? I'm wrong. It's wrong here that we're not scaling the features, also because we are using SVM in this first example as classifier. But I repeat, this is just an example whose goal is to show you how to perform cross-validation with more than 1 hyperparameters, okay? It's not to do a real analysis, okay? So after this caveat, we can see what's going on. So I repeat, we use SVM to try to classify the wines. In SVM, this is non-linear SVM, so it's kernel SVM. The scikit-learn function SVC uses as default the RBF kernel. And so if you remember, for this classifier, we have 2 hyperparameters, the C hyperparameter, which tells us like how much we are willing to pay in order to have misclassified units, and so it regulates, the size, the distance of the margins from the decision boundary. Okay, while the gamma hyperparameter regulates the width of the RBF kernel of the almost Gaussian function, let's say, of the Gaussian, the width of the kernel. Okay. So, and also here, if you don't remember the meaning of these hyperparameters in detail, then come back to the kernel SVM lecture and read it. Now, to do this, we tune the C hyperparameter with such values that I'm highlighting, and the gamma hyperparameter with these other values. Okay. Okay. Yes, I'm gonna give you a remark, but after we see this example. So here what is done is we use a grid search, okay, which means we are gonna try all possible combination of hyperparameters that we have specified. And the result is telling us that the best like among the tested one, the best set of hyperparameter is C equal to 1000, so pretty large, and gamma pretty small, okay, equal to 0.000001, which leads to a result on the test set of 0.85. Also here, I'm giving you this test set just to show you how it works, but always remember that the test set must never be checked for model selection. Okay, you should always do model selection with cross-validation or with the holdout set. Okay, and only after you have selected your model, the best model, then you assess how it performs on a separate test set. Okay, this is very important. And the other remark I wanted to give you is the following. An alternative to perform cross-validation like this, or actually an extension, is to say, okay, let's start with this parameter grid that we have here, specified here, for example, for the C values. Okay, as you can see, we are using quite a large range because we start with 0.001 and we end at 5000. What we can say more is, let's first try the order of magnitude around which cross-validation tells me the estimator, okay, SVM might perform better in this case. And in this case, it turned out to be 1000 for the C parameter. And then what we can do, we can try to run a second step of cross-validation and say, okay, now let's look for values of C that are, closer to 1000. For example, between 500 and 2000, for example. And so let's search in this smaller space. If you want, you can further go on, okay, and let's suppose the next best value is about 900, and say, okay, let's search between 850 and 950, okay, and we can continue until we find, the best value, zooming in more and more around the region that cross-validation indicates to us, and this way of searching, with cross-validation is called zooming in, or is also called telescopic search. Okay, but these are just details that I think it's important for you to know. Alright, so once we have observed the best results, we can of course list them exactly as was explained in the model selection notebook. We can also, in this case, since we just have two hyperparameters, we can use a heat map to see the results in 2 dimensions. Here I report a small function which I took from a library on GitHub. I report a small function that allows plotting the accuracies, the scores in this case, for different values of C on the y-axis and gamma on the x-axis. And as we can see, the best value is reported to be 0.94. Okay, and this is useful to give an idea in what regions, you know, of the space our estimator is performing best. And this is clearly saying that if let's say gamma is smaller or equal than 0.0001 and larger or equal to 100, then we or actually also gamma larger than 1 to 1 to the minus 10, then you see in this area we have the best results. And so an idea is the next step, let's try to focus more in this area, okay, to zoom in how cross-validation, what cross-validation says when we, you know, perform the search in this area. Okay, here I report another example with randomized search. For randomized search, we can also you know, specify an array of values, in which case they will be randomly sampled by randomized search. Alternatively, we can just give a probability distribution, okay, with a given position and scale, which reflects our prior ideas about where hyperparameters might be located. And then we can let randomized search just randomly draw from these distributions. These distributions are specified with the stats module of the SciPy library. And in particular, I use an exponential with scale 1000 and a gamma, and another for the parameter, and a gamma, for gamma, another exponential with scale 0.001. Okay, and in this case, I'm saying, okay, I think C, search for C around this large, you know, area, and search gamma around this smaller area. And the results, as you can see, are of course different. They are searched about across 100 iterations. Of course, the larger this number, the more the higher is the probability to find a good set of hyperparameters. We're going to use 5-fold cross-validation, exactly what we have done also for grid search. And you see, in the case of grid search, the best results were 1000 and 1 to the minus 5. It's 10 to the power of minus 5. Here we have 823, which is not the different, and also the value for gamma is not too different from the one we found with grid search. Okay, and let's compare the results on the test score. Here we have 0.85, which is exactly the same we obtained with randomized search. Okay. And only the cross-validation score is a bit lower, but of course we cannot compare these two scores because it's two different ways to perform model selection. So every time you perform an analysis, you have to choose beforehand what model selection procedure to use, and then use it across the whole analysis for all estimators you need. Okay, you cannot say I want to use cross-validation for an estimator and hold out for another one. And also you cannot say I want to use you know, 5-fold cross-validation for an estimator and 15-fold cross-validation for another one. This is not how it works. Of course, you can use different model selection methods, but you have to do it for all the models that you choose, okay? And then try to think well about how to pick the best model. Okay. Okay, we can also obtain the best results. In this case, they are sorted by, you know, you see by rank. Okay, so that we have the best cross-validation score accuracy in this case, which is the default for classifiers, on top, and here we have listed the top 5. And we can also plot in this case we cannot use, it doesn't make sense to use heat maps because we are not searching across a sorted list of values, but we are randomly picking every time pairs of values that are not necessarily sorted. But what we can do is we can plot the cross-validation scores, the cross-validation accuracies, and sort them by by rank, exactly as we have reported in this data set. Okay, and so now we can see a nice comparison of these best estimators. Okay, also as an extra point, we can check what the best parameters were. You see the best two hyperparameters for C are around 820, and the best parameters for gamma are all around 10 to the power of minus 5, are in that order of magnitude, meaning that we really need a small gamma for this data set. Okay. Now let's go. There is also an example with 3 hyperparameters, and in this case what we are also tuning is the kernel. And in this case you have kernels that use different hyperparameters, because the RBF use C and gamma, as we have seen, while the linear kernel, which is the other hyperparameters we are tuning, only needs the C hyperparameters. And so what we do in this case is to create dictionaries of list of dictionaries of list of hyperparameters, where each kernel in this case has its own dictionary. And for example, grid search will search across all these dictionaries, while randomized search will first randomly pick one dictionary and then we randomly pick values from the dictionary. Okay, and this is how it works with 3 hyperparameters. Of course, if we had the kernel that was polynomial, okay, we could add another dictionary, for example, and specify the C hyperparameter and the degree of the polynomial as another hyperparameters for this kernel. Okay, and the rest works exactly as we have seen so far. The best set in this case we see with grid search is the linear kernel with C equal to 1, which lead to a very good cross-validation score, and indeed it seems to be the best kernel in this case. And that's it. I didn't do it with randomized search, so I invite you to try at home. Try to just modify this grid search with randomized search and see what happens. Try also for a quite large number of iterations if you have time. It shouldn't take too much in this case. Okay, so this was the first example. Now let's go to example number 2, and here I would like to start with some explanation. I mentioned this sometimes during class, but I never went too much in detail about it. So the thing is, every time we wanna make model selection and we have preprocessing methods to run on our dataset, like a common mistake that is done by students, but not only by students, also by true machine learning practitioners, is, okay, let's do preprocessing, okay, and then with the preprocessed dataset we do model selection. And this is wrong. In particular, this is wrong because it can lead to too optimistic results. And in order to understand this, you have to see this fact. So when you if you do like in this way, like you perform preprocessing and then you do cross-validation, you are implicitly assuming, because when we do the preprocessing we are estimating parameters, okay, on the data, we are implicitly assuming that that the values that actually not too implicitly, we are explicitly assuming that the values of these parameters are calculated also using the validation set, okay? For example, let's say we wanna impute some missing data. When we make missing data imputation, of course with the mean, okay, or the median of a variable, then we need to first estimate the mean or the median of that variable, okay, and then impute the missing data, the missing values with that mean or median. However, if we do it on the whole data set, we are basically saying, okay, to calculate this mean, I'm also going to use the values of my test set or of my validation set, okay? Which is a way to say, okay, I already know the future. I already know what my future data that I want to test or that I want to predict will look like. But when you are in a real situation, you don't know beforehand the values of your future data, okay? So if you do model selection in this way, then what you risk is to obtain too optimistic results from cross-validation, because you're using values estimated with the validation set or test set to make predictions of the median, for example, on missing values, also on the training data set, okay? And this could lead to inflated values, you know, too optimistic performance of our cross-validation score. Another example, and for this example I invite you to read this section 7.10 page 242 of the elements of statistical learning, which is a great book, by the way. It's a bit too like it's a bit big, you know, a lot of pages, but I just put some link every now and then to this book because I think it's great to understand the theory behind data mining and machine learning. And so in this book, in this page, you can find an example on how to do cross-validation with feature selection. And you can imagine if you do feature selection and on the whole training data set, okay, and then perform cross-validation, then you will definitely obtain too optimistic results. And this page of this book explains this very well, so please read it in order to understand the concept. So you might wonder, so what is the right thing to do when we want to do some pre-processing and then cross-validation? Well, first of all, you have to do a mental step, and you have to always imagine that you are in a situation in which you only know your training part of the data, okay? So for example, let's imagine holdout validation. We have a training set and a validation set, okay? In the wrong way, we will use the whole data set to perform feature selection or the missing data imputation, okay? But in a real situation, you always have to pretend you don't know, okay, the values of the validation set. You only have the training set, okay? So what you have to do is you do feature selection on the training set or data like median or mean estimation for missing data imputation on the training set, and then use the estimates obtained with this training set and implement them on the test set or on the validation set. Which means, for instance, I'm doing feature selection on the training set. I'm on the training set. I'm estimating. I'm finding out that I can remove from my data set features 5 and 10, for example. Okay, then the next step is you take your validation set and you remove features 5 and 10 from this data set, okay? Now, for cross-validation, it's the same principle, but you have to do it at each fold. So for example, I have my first fold in which I have a training, my first iteration, I have a training set and a validation fold, okay? You do feature selection on this fold and you remove it from this data, from the validation set. Then for the next fold, you might find different results, but then you still have to apply them to this validation fold, and so on. And you repeat the process for all the false. Okay, so it's basically doing holdout, but at each iteration. It's true that you might end up with removing different features at each iteration, but I want to remind you that the goal is to find good hyperparameters and good parameters of the estimators, rather than performing the proper feature selection here. So for example, if cross-validation is telling us the best thing to do with this dataset is to remove 3 features or 5 features, then this is what you should do. Okay, and then once you're done with cross-validation, you use the whole training set. Okay, you rerun your feature selection method, and you remove only features 3 and 5, sorry, 3 or 5 features, depending on what cross-validation has told you to do. Okay, I hope this was clear. Now, what we're gonna see in this example is we're gonna chain 3 operations in order to show you how to do this in practice. Okay, with cross-validation. Once again, I know I don't need to repeat it, but it's always good. I'm gonna use cross-validation with grid search. You can also do it with holdout. You can do it with a randomized search, and so on. Whatever you feel like it's the best option. All right. So in particular, we're gonna see whether we prefer to do data scaling, okay, with the normalization with the min-max scalar transformer of scikit-learn, or with standard scalar, so with standardization. Then we're gonna see how to perform feature selection with select k-best and different number of features to select. Okay, so this is the hyperparameters in this case. And then we're gonna chain these operations with k nearest neighbor, in which we tune the hyperparameter k. Okay, in the notebook you will find more information about exactly what hyperparameters we're gonna use. Here I'm focusing more on the steps we are gonna take. So first of all, we need to create a pipeline, okay, with some values initialized. It doesn't matter which values, because we're gonna tune them anyway, but you need to put some value. So if you remember, a pipeline takes a list of tuples, and each tuples contain the name, which can be arbitrary, you can give any name you want, the name of the operation you perform, and the estimator or transformer of scikit-learn initialized with some value. Then we use select k-best for feature selection. Of course, you can feel free. You can even tune what is the best feature selection method to use. But here we're gonna use this specific one, and to decide which features to retain, we're gonna use the f value for classification. I think I explained this measure during the lecture on data preprocessing, but if not, you can simply go to the scikit-learn documentation, and in the I think both in the select k-best, but also in the f, and for sure in the f-classif function documentation, you will find all the information you need. Anyway, once again, this is secondary now. I just want to focus on the operation we're going to take. And then the next operation we're going to do after scaling and feature selection is, so you have to imagine we scale the data, we select the best features, and then we run k and n on this subset of features. Okay, and the next step after initializing this pipeline is to create the proper parameter grid. And to do this, we in this case we create a dictionary, okay, where the name of each, the key of each element of the dictionary has the same name given to the elements of the pipeline, and for each of these elements we give a different hyperparameter or even a different estimator. In this case, you see we are choosing whether min-max scalar or standard scalar should be used for this dataset. After that, we simply call grid search CV, giving our pipeline as estimator, okay, and the parameter grid that we just created. And so grid search, we start looking across all these methods, and in particular, we'll also search whether 1, 2, 5, or 10 features are the best, is the best number of features to retain. Okay, and then after we have done all of this, we see that the best pipeline to use led to a cross-validation score of 0.98. Okay, so even larger than the previous one. We selected 5 nearest neighbor. Let me check. Yes, 5 nearest neighbor for the KNN classifier. Min max scaler was the best scaler for this dataset. And for the number of features to retain, 10, k equal to 10 was the best number in this case. All right, when you do this, I also suggest you to, it's not done here, but also try to put the number of all the features you have in your dataset to see whether maybe it's better not to use feature selection in this case, because if the best k results to be equal to the number of features, then in that case, it doesn't make sense to do a feature selection. There is also an alternative way, but we're gonna see it in the next example. You can also retrieve the name of the steps produced by the pipeline by calling the named steps attribute of the pipeline. I think this is also what I'm doing in the exercise 4 of homework 3. So keep in mind what this does when you comment the exercise. And this is it. And then as usual, we can plot the best results. I leave to you the comments, in this case. You can see what's the ranking of the best K for feature selection, of the best K for K nearest neighbor, what was the best scaler. In this case, we only show the first 5, but of course you can extend the list by giving a number here to the head function. Okay, and if we can also see what features have been selected by the feature selector with the best estimator in this case, by simply calling the best estimator of our grid search estimator. Okay, so this is the attribute of grid search, and since this is a pipeline, we can call the named steps of this pipeline. We want to see the selector one, which has the attribute scores, and the scores give us the scores of the best of all features, and based on this we can see which are the best 10 features selected by our feature selection. Okay, and these numbers are the F measures for classification that we have used. Importantly, another thing you might remember from data preprocessing lecture is that we have used imbalanced learning in case of imbalanced datasets. Of course, you can also, and you should always use this as in a pipeline because of the same reasons I've told you in the introduction to this section. So if you want to use the imbalanced learn library in order to rebalance your dataset, you always have to do it within cross-validation. Okay. In order to call these imbalanced learn methods in a pipeline, you have to use the pipeline created by the with the imbalanced learn provided with the imbalanced learn library. Otherwise, it doesn't run in the scikit-learn cross-validation. But the functioning of the two pipelines is the same. So once you create your imbalanced learn pipeline, then you can put all the scikit-learn methods you want also in in that pipeline, okay? So it shouldn't change too much. Yes, so this is it. This is what I wanted to say. Now, last example. Here we are once again gonna chain pipelines and estimators, but this time we're also gonna compare different estimators. In particular, we're gonna compare a logistic regression with k-nearest neighbors. And just to show you an extra option you have, we're gonna use only some pre-processing steps with one estimator and other pre-processing steps with another one, so that you can see how it works. So once again, we initialize our pipeline, you see, with the pre-processing and classifier. In this case, we only use one pre-processing method, but you can use at least like a lot of them if you need. We use k neighbors. So as classifiers, we use k nearest neighbors on the one end and logistic regression on the other end. I also set a large number of max iteration to make sure it's gonna converge. And as you can see, we create a dictionary for each classifier in this case. And if you can see, with k-nearest neighbor, we say, okay, we don't want pre-processing here. Use k-nearest neighbors without pre-processing. While for logistic regression, choose between standardization, normalization, and no pre-processing. Okay, so we have this option by giving the non option to scikit-learn. Okay. Of course, this is not a very fair comparison. We should always use or try to use similar pre-processing techniques for each estimator, but we also have to take into account that every estimator might require different pre-processing methods, as we have also discussed during lectures. So keep this in mind when you do your analysis. The rest occurs exactly as we have seen. We run grid search. We feed the data. Grid search with this pipeline on the data and with this parameter grid. And we obtain a cross-validation score of 0.98. Okay, notice here we are comparing estimators also. Okay, so keep this in mind. Notice that I'm not touching the test set here, and this is how it should be done and how it should have been done also in the previous examples. Okay, so not touching the test set. We can see the best hyperparameter set. The best model is logistic regression with C equal to 10 with the standardization pre-processing step. Okay, and this is our best model found by grid search. Now, what we can see in the results is that, let me see here, you see all the five best ranking models are all logistic regression. And in particular, we see that model 1, the first two models rank the same, they have the same cross-validation score, but they have different values of C. One is 20 and one is 10. Where 10 leads to a simpler model and 20 to a more complex model. Now, what we're gonna do is we're gonna say here, are the two models just, statistically different, or they're statistically equal? So we want to try to say if the differences observed in these first two models has some statistical significance. And this can be done, of course, also between model 1 and 3, model 2 and 4, model 1 and 4. You can compare any pair of model you want. To do this, you could use the t-test, right? For the comparison of means, because you also have the cross-validation standard deviations. And how to do the t-test, I left a link here in the notebook. But what I'm gonna do here instead is what is called a McNemar test. Why a McNemar test? If you don't know what it does and how it works, I also left a link here. But basically, it's like t-test, okay, a paired t-test, paired samples t-test, in which takes into account that the data are somehow correlated with each other. Okay, because the results we obtain from fold to fold in cross-validation have some correlations because they are sharing some observations. Then in this case, the McNamara test is the way to go with interpretations similar to the one of the t-test. Anyway, you can find the link here that explains to you better. So what you do is you run the two pipelines. We write the two pipelines with the best, with the two models we want to compare with their steps. And then we use the predictions of the model, okay, obtained with cross-validation for these two pipelines. And we use this prediction. We will perform a t-test, a McNamara test actually, on these two columns of predictions basically. And so what we obtain in the end is a p-value of 1 in this case, which of course it will happen because the two models lead to exactly the same cross-validation score, but this was just a way to give you an example on how to perform a test when comparing estimators. And because the p-value is smaller than 0.05, for example, if we use a significance level of 0.05, then we reject the test. We say that the two estimators are equal. And in this case, we decide to continue with the simpler model, which is the one with C equal to 10. Right? Oh, sorry, C equal to 0.5. Why 0.5? Oh, okay, my mistake, sorry. Basically, I'm comparing C equal to 10, which is equal, of course, to the one equal to 20, with C equal to 0.5, which is the third best estimator. And you see it's only slightly worse than the other two, and that's why, okay, now everything makes sense. Sorry, it was my mistake. We are comparing basically this estimator with this one, okay, number 2 with number 3, because number 1 and number 2 are the same. We pick the simpler model with C equal to 10. In this case, we compare then logistic regression with C equal to 10 with logistic regression with C equal to 0.5. All right, and so the results are still telling us that the two models are statistically equal. They lead to statistically equal predictions. So we can continue with the simpler model, which is C equal to 0.5. And so the next step we do is we compare this best logistic regression model with the k nearest neighbor model, okay, which is k nearest neighbor with k equal to 1, which is the best performing one. Maybe you cannot read it sorry very well from this graph, but if you explore better this data frame of results, if you continue if you use a larger number of rows to visualize, you will see that the best model is k nearest neighbor with k equal to 1. And so what we do is compare statistically that with the best logistic regression model we are chosen with the McNamara test, so C equal to 0.5. We compare them, and what you see is that this time there is statistically significant difference between the two models. And so we simply say, okay, logistic regression in this case is the clear winner. And this is it. So this is our final chosen model. And what we decide to do, then we implement this best logistic regression model with C equal to 0.5 to the trained set to see the score. And you can see that it leads to a very decent, very good score on the test set. Okay, so this is how you should perform an analysis. Maybe performing the test is not always necessary. You can also just use the cross-validation score, pure as it is. But if you see, for example, like in this case, that the variance of one, the variability of one is telling, look, maybe I could, be equal somehow to the best performing one, then doing a test never hurts, okay? And alternatively, you can use the t-test. This was it. We can also see a confidence interval of the accuracy, in this case, on the test set, which ranges in this case between 0.85 and 0.99. Also, this is not necessary, but it's nice to have also statistical, estimate, like an estimate of the uncertainty of our score on the test set. This is it. You will find more information on this notebook. I will also give you some extra exercises to play around. The one that I care the more that you could try to do is A, because in this case we have seen logistic regression with preprocessing against k-nearest neighbor without preprocessing. Okay, so in this exercise you're asked to implement preprocessing also for k-nearest neighbor, and then try to compare the new results and perform tests if necessary. Okay, and then you have other exercises you can do whenever you have time, which I hope you find useful. Okay, this was it. This was what I wanted to tell you today. I hope you found this lecture useful. Thank you for your attention. Thank you for watching. And now I'm gonna record another couple of lectures we still have, but I will upload them next week when is the right time for these lectures. Okay, thank you again, and good luck with the assignment, with the homework. And I want to remind you, Sibylla and I are always open to answer your questions, so please don't wait the last day before the deadline to write us, okay? Always write us in the like when you have time also to work on the assignment then. Okay, good luck again, and have a good day. Bye.